Good morning, ladies and gentlemen. I hope you guys are doing well. So today, as you can see, we're going to be starting our new unit, the unit on work, energy, and circular motion. Normally, what I would do in class is we would be doing these as two mini units, but because COVID sucks and we're not at school, I've combined this into one unit, and we're going to be doing kind of a little bit of everything throughout. And we're not going to be your assignment isn't going to be as big as the two I would normally give, one on energy and one on circular motion. So it's going to be a little bit toned down from what it would be, and I'm just going to kind of be picking the bits that you're going to need the most of for Physics 30 out of this. So that's kind of how this is going to work. I'll be posting your assignment soon, as at the moment it's something foolish like 35 questions, which you don't need to do 35 questions on this right now. So once I get that sorted out and played with, then I will get that posted for you. So in the meantime, we've got your lovely work notes. As well, because of the I haven't given you the lovely, thick, beautiful package of paper that I normally would give you for your notes for the unit. What I'm going to be doing is I'm going to be posting each set of notes per topic with the video on Google Classroom. So if you're watching this on YouTube, make sure you go to Google Classroom. So pause it now, go to Google Classroom, print out these notes, and then, or put them on your iPad or whatever, so you can take your notes that way. And of course, the pun, it had to happen. Get it? Too much negative energy here? False. Energy is a scalar quantity. Energy can't be negative because it's scalar, no direction. Please tell me you're laughing. Okay, good. You are. All right, even if it's at me and as opposed to at the joke. So, ladies and gentlemen, let us begin with our work topic. So, ladies and gentlemen, I'm fairly certain that you guys remember at least the idea of work from last year in Science 10. The equation is on your data sheet under, I think it's under work. It should be under work and energy section of your data sheet. Where is my data sheet? I have like 6 of them flying around here. And of course, it's never where I need. They're never where I need them when I need them. Yeah, there we go. Okay, so on your data sheet, your work equation is right there. Okay, you see it? Right under there. It's under the momentum and energy section. There's a whole, remember this is a grade 12 data sheet for Physics 30. All the equations you need are on here, but there's a bunch of other stuff that you don't need. So much of this stuff you're not going to need till next year. Okie dokie. So with this one, we have work equals force times distance cosine theta. Now, the cosine theta part is the new piece that you wouldn't have looked at last year. Last year, you just saw work equals force times distance. So we're going to talk about that cosine theta a fair bit today. So as per usual, force is in newtons. Distance is displacement. Work is in joules. So it's a type of energy. And theta is the angle between the force and the displacement vectors. So we're going to talk quite a bit about that today. Okay. Now, work is a scalar. All energy is scalar. That's why I picked the meme for this. I don't know. Yeah. Okay. And the force, it can be any kind of force. Force of gravity, force of friction, force applied. You pick. No? And over for Physics 30 next year, we got magnetic force and we got electric force. It could be those. Any force, doesn't matter. Okay? And one of the things that maybe talked about a bit as well is network. So you can have work that cancels itself out the same way a force can. And it can be done on objects to change their velocity because there's a net force acting on an object. So if we have a net force, we can have net work. So that's something we'll talk about a bit later as well. So Remember, ladies and gentlemen, that from last year, when we have work, we have to have an object that's moving. So work is equal to force times distance. So right now, what do I have? I don't have my tea travel mug with me. I still have a mug of tea. So if I put my mug of tea onto my notes here, and I apply a force to my mug, well, it's not moving. So therefore, I haven't done any work on the mug. So you have to have distance for work to be done. Okay, so if you push on a wall, you are not going to be doing work on the wall unless you're the Hulk and bash over said wall. And my tea is cold. That's okay. So, ladies and gentlemen, let us look at a couple of different scenarios that are going to be different from what you did last year when you were looking at work. Okay. So I want to, it says 3, but I'm actually going to draw 4 because I can. So we're going to be talking about some displacement here. So the first thing we're going to be looking about is the standard work scenario that we would have talked about. Here's your object, and we are going to be having our motion going that way. Okay. Well, if you apply a force here, your force is going in the same direction as the motion. You're going to be pushing or pulling that object to cause it to move in that direction. So, a couple of key points. Our vectors here are parallel. When you have two lines like this, remember from the inclined planes, you had your FG parallel and FG perpendicular. Well, the two lines being parallel. So our vectors are parallel to each other. And because of that, your theta is going to equal 0 degrees. As motion's this way, force is this way, there is no theta, there is no angle. So I want you guys to take your calculator and making sure it's in degrees. If your calculator's not in degrees, you're going to have a rad time. Get it? Get it? Calculator being radians? Yeah. Put your calculator in degrees, please. Okay. So when you put in your calculator cosine theta, what do you get? Cosine theta. Cosine of 0, what do you get? 1. Well, cosine of theta is 1. Well, when we look at work equals force times distance times cosine theta, well, work equals force times distance times 1. And that's just force times distance. That is what you guys were looking at last year. You guys were looking at work as force times distance because all the scenarios you were given is where theta equals 0. Yeah. Cool beans. Okay. So, ladies and gentlemen, that is something to keep in mind, that cosine of theta equals 0. So then now, cosine of theta equals 0. Let's try this again. Cosine of 0 equals 1. So then when you are going to be dealing with your force and your motion as completely parallel, then we have just work as force times distance. Okay? Another thing that we're going to be talking about as well, that is not the arrow. There we go. Another thing we're going to be talking about as well here is whether work is going to be positive and negative. Now, remember, ladies and gentlemen, how with our meme, we can't have negative energy because energy is scalar. But we often, in both chemistry 30 and in physics, you are going to be assigning positive and negative values for energy concepts, for energy numbers like work or energy transferred, enthalpy, whatever. And that is just kind of give it an idea as to its role. So when we talk about positive work, what that actually means is that the energy is being used to cause displacement. Okay, so it's causing displacement. It is causing an object to move. It's causing an object to accelerate. So that is the key piece there. So when we're dealing with positive work, it's saying, well, this is what the job is doing. It's causing motion. It's causing displacement. It's causing something to move. Okay, so positive work is just a notation as to its job. Energy can't be negative. Energy can't be created or destroyed. And if we had negative energy, then it would be destroyed. And that would be disrupting the laws of thermodynamics. And we do not disrupt the laws of thermodynamics, ladies and gentlemen. It just doesn't happen. Okay, so that's one scenario. The second scenario I want to talk about is our negative work. So if our motion is going this way, that's supposed to be an arrow, and we are going to be having a force going this way. Well, that is our force of friction, or most of the time is going to be our force of friction in our case. So when we have force of friction here, this, ladies and gentlemen, is going to be negative work. Okay, because it is opposing displacement. Okay. It is opposing motion. Okay. It's hindering it. It's preventing that movement. So it's still technically positive because it's still there. It's not a disappearance of energy, but that negative sign is just telling you its job. It's stopping movement. So now I want you guys to think about the vectors. Are these vectors parallel to each other? Yes, they are. They are parallel vectors, so that means theta is going to equal 0 degrees. And, oops, let's try this again. Okay. So, okay, let's try this again. So now let's actually look. We actually do have an angle here. It is no longer completely 0. I'm going to redraw this little blue arrow here to represent velocity. This blue arrow is not force, it's just velocity, so it's easier for you guys to see what's happening. Well, I'm going to take my pink here. Well, what is the angle now between this? 180 degrees. They are parallel to each other, but they're going in opposite directions. However, in this case, our theta is 180 degrees. Now, this is what's going to show you mathematically why work is negative. Okay, not just the fact that it is. Okay, mathematically, how do we get that negative work? So, how we get it is, well, I want you guys to put into your calculators cosine of 180 degrees. Well, once you do that, you're going to see it's going to be -1. Well, work is force times distance times cosine of theta. Cosine of 180 is -1, so work equals force times distance times -1. So once you multiply your work times force times distance times your -1, you get that negative value for work. And that is the mathematical reason for why work is going to be negative. Okay. And remember, negative values of energy is not a lack of energy. It's just telling you its job. Okay. That's just telling you the job of that energy. Okay. Now, another scenario we're going to talk about is a force that's not acting parallel, a force that's acting perpendicular in this case. So here, let's put force of gravity here. So force of gravity is going this way, and our object is going to be moving that way. So, well, let's look at these. I'm going to redraw my velocity here so that it's this way. This is not a force, this is velocity. Okay, so that way it's just easier to see here. Well, now I'm going to draw my theta here. Now look at that. There's my theta. The angle between these guys is going to be 90 degrees. There you go. Okay, so please put into your calculator, ladies and gentlemen, a cosine of 90 degrees. And what do you get? 0. So ladies and gentlemen, cosine of 90 degrees is 0. So that means if work equals force times distance times cosine theta, and I need to scroll down so I don't write on my face. There we go. Writing on my face generally only happens if I have like ink on my hand and then I touch my face and I'll have like an ink spot on my face all day. Or if you put a pen in your hair and then it like draws on the back of your neck. That's happened too. Okay. All right. So when you put these numbers in, so your work equals force times distance times 0, well, that means work is 0, so no work is done. Now, no work is going to be done by that particular force. So, well, let's look at this scenario and see why it makes sense. So, force of gravity. Force of gravity is pulling downwards. So if I grab my mug of cold tea again here, okay, and we look at the mug of tea on my notes, well, we push this. Well, gravity is absolutely working on this. But right now, is gravity continuing to my mug's motion? No, it isn't. It's the force that I'm applying to the mug sliding it around. So that makes a lot of sense there. So if you are going to have 90 degrees, you are going to be having your no work being done by that particular force. If there's other forces acting on it, then absolutely there could be work done. All right. So there's another scenario I want to talk about as well. I'm going to grab my eraser here and I'm going to try and get rid of this stuff so I've got more space to write. Now, this is the scenario where you're going to have our forces applied at an angle. Now, we've already talked about that. So you guys remember with from back in the dynamics section where we had force applied X and force applied Y. So that is where our force is going to be applied at an angle. Okay, so that's where we have that guy there. Well, this is your force. There we go. And if that is the speed in which the object is, or direction the object is moving, well, look at that. That is going to be your theta. As your speed, I can redraw that in just a slightly different position to make it easier to see. The speed is going that way. So the theta between the ground and your force is going to be your theta. So while y, this is where also it comes up the question, well, why is it cosine? Why isn't it sine? Well, work is equal to force times distance, cosine theta. Well, let's think about cosine for a sec. Cosine of theta is equal to your adjacent over your hypotenuse. Well, here, look, the force that you're going to be applying is going to be the hypotenuse, and it is going to have x and y components. Well, cosine is your adjacent here of your triangle. Now, it is the force applied on that x, which is this guy, remembering back from that other video that we did earlier in dynamics. Yeah? Your forces applied on 2D. Yeah? Okay. So this guy is the only part that is actually contributing to the motion of that object. Your force applied on the y is going to be changing the normal force. It's going to be impacting the friction, but it's not contributing to the displacement of that object. It's only on the y. And guess what? If I'm going to get my force applied on the x, I would take my hypotenuse, which is my force applied. I want to find what my force applied on the x is. Well, that's adjacent. So it would be my hypotenuse is force applied. So I would have my regular force applied, and then I would be multiplying that by cosine of theta, and that would give me my force applied on the x. Well, look at this, force applied cosine theta. Force times distance times cosine theta. It's the same thing. I could just rewrite, and because we're multiplying, I can put these values anywhere I want. Like I could go work is equal to force cosine theta distance, and it's the same thing. So because when you multiply numbers together, you can put them in any order. So that is where this equation comes from. Isn't that awesome? Yeah, I think it's super cool. So in this case, the work is going to be done is entirely based on the force applied on the x, and that comes from cosine theta. Cool beans? Cool beans. Okay. So ladies and gentlemen, enough of direct instruction and you guys simply listening to me natter. Let's do some calculations. Okay. All right. So, coal exerts a force of 20 newtons to push a 55 kilogram crate 1.35 meters along a horizontal surface at a rate of 2.7 meters per second. Okay. Calculate the work coal does on the crate and calculate the work done by friction on the crate. Okay. So, tip. This is physics, guys. Remember how when we started dynamics, we kept bringing stuff from kinematics in? Now we're going to be bringing in kinematics, dynamics, all into our energy equations. You guys excited? I'm excited. Okay, so we have our force applied here, which is 20.0 newtons. And we're going to be pushing a crate with a mass of 5.50 kilograms. And our distance is 1.35 meters. Okay, at a rate, note the units, ladies and gentlemen. Look at those units. Meters per second squared, that's acceleration. Please don't put that down as meters per, don't put that down as V. Watch your units very, very carefully, guys. Okay, it will make me sad inside if you write it down as V. Okay, so our acceleration is 2.7 meters per second squared. Okay, so ladies and gentlemen, let's think about this. We've asked to calculate the work that coal has done on the crate. Okay, well, let's look at our work equation. Work is equal to force times distance times cosine theta. All right, well, we have the forces applied. Okay. Good. And we've had the distance that he's covered. Okay, good. Well, cosine theta, let's think about this for a sec. If the crate is being pushed, let's say that way, along a horizontal surface. We are pushing with the force applied this way. Well, these guys are parallel to each other, so that means theta is 0, so that means cosine of theta is 1. Okay, so theta is equal to 0, cosine of theta is 1. So that means we can just cancel out this cosine theta now, okay? Because work as force times distance times 1 is exactly the same as force times distance. Okay, so that's 1, so it cancels. Okay, now that's very different from what we've done previously. Before, we're just like canceling stuff out with zeros. Notice when I canceled it, though, I did not cancel out the force times the distance. That's still there. The cosine of theta isn't, okay? Because it's force times distance times 1. If you still want to put it in there just to remind yourself it's still there, you absolutely can. Okay, so he did 20 newtons of work over a distance of 1.35 meters. So that means, and that's for A, that when you multiply those together, the work was done, it was 27.0 joules, 3 sig digs. Now, ladies and gentlemen, work is scalar, energy is scalar. So that means you do not give me a direction, please. I only want direction on vectors. Energy is scalar, as the meme on the front of your notes explains. Yes. Okay. So now we need to look at the work that was done by force of friction. Now, well, how are we going to find what force of friction is? Just like you did in the previous unit. We're going to make an F net equation. All right. So, ladies and gentlemen, our F net is going to equal the force applied minus the force of friction. Now, what I'm going to be doing from now on with our F net equations is I'm going to make the assumption that you're comfortable with them. Okay, because we're now going to be looking at other objectives and just kind of using these to help us. So if you are still having a hard time with making FNet equations and that kind of thing, make sure you sign in on office hours so we can work on those, okay? Because I'm just going to be treating the FNet equations as if you're comfortable with them now. Okay, so I'm going to try and get my force of friction. So I am going to rearrange this, and there's multiple different ways you can do this. I've done it many different ways in the videos. This time around, I'm going to change things up a bit. I'm going to add my force of friction over. That cancels. So then I'm going to be left with force applied is going to equal my FNet plus my force of friction. And then I'm going to subtract out my FNet. So by doing this in 2 steps, it means I'm going to be left with a positive number for force of friction, which just makes it a bit easier. Okay. And you're also welcome to rearrange it the other way if you so desire. I know I do that all the time. Oops. Erase. So my force of friction is going to equal my, ladies and gentlemen, force applied minus my FNet. So, well, I have my force applied. That number's been given to me. My FNet, well, how am I going to get that? FNet equals MA. Very good. So I'm going to replace that FNet with my MA. Well, I have been given mass, I've been given acceleration, so we're good. I can now go and put my numbers into my equation. I'm just going to move up here. So my force of friction is going to equal my 20 newtons minus my mass, which is your 5.5 kilograms, and that's going to be multiplied by our 2.7 meters per second squared. Now, be very, very careful on this one, ladies and gentlemen. Watch your bed mass, okay? Make sure you use your brackets, do the multiplying first. So once you put that in there, we're going to get our force of friction as going to be 5.15, newtons. Okay, so let's think for a moment here. I'm going to draw what's happening. A little free body diagram here. Motion's this way. Friction is this way. Theta between motion and friction is going to be 180 degrees, as we talked about earlier in the video. And cosine of 180 is going to equal -1. Okay, so it means our work is going to be negative. So, ladies and gentlemen, the work done by friction is force times distance times cosine theta. The work of friction is going to be the force of friction, so 5.15. Okay, that's the force applied. Now, the distance that that object moved was still 1.35 meters. Okay, and cosine of theta, so cosine of 0 is -1. Now, I'm going to scroll down here so I can still write. There we go. So the work done by friction is going to be, once you plonk those numbers in your calculator, is -6.9525 joules. Okay. Now, ladies and gentlemen, once again, remember, negative isn't direction in this case. Negative is the job that it's doing. Okay, so the work done by friction, and once we have all of our appropriate sig digs, -6.95 joules. So leave that negative there. Don't turn it into a direction, because this work is the work done by friction, essentially an idea of the amount of stuff that friction stopped the guy here, Cole, from actually doing. Okay, so it's negative. That's the amount of energy that was used to hinder motion by friction. Okay, so once again, negative work is its job, is the job of hindering motion. It is not the direction. Now, if I say something 60,000 times and repeat it again and again and again, you think it's important? A little bit. Little bit. All right. So, ladies and gentlemen, let us go and look at question number 2. In this case, we're going to be pulling in some kinematics. Yeah. You guys don't sound super excited. We're going to have kinematics and dynamics, and we're going to have energy equations. Oh, yeah. Come on, more enthusiasm. More enthusiasm. Cheers, yeah. All right. Enough of me being silly. Yeah, that'll last 5 seconds. Okay. So there's our object. Okay, we're going to draw our free body diagram, or at least the part that we are going to need. So let's list out what we have. A 1,385 kilogram car traveled at 61 kilometers an hour. We're going to have to convert some units, guys. Your favorite. And brought to a stop. Okay, that means VI, VF. Remember, ladies and gentlemen, VF is 0. One thing to keep in mind, when you see the keyword stop, that 0 doesn't mean sig digs, okay? So the word stop or rest does not impact your sig digs, okay? So I've seen that show up a couple of times when marking some previous assignments. So I dropped a P. That says impact. So the word stop does not impact sig digs, okay? So I've got my M, I've got VI, I've got VF, I've got a distance of 42 meters. And what is the work done on the car by the frictional forces? Okay, so we need to calculate work. Well, the car's velocity is going this way. It is slowing down. So that means its net force, so force of friction in this case, is going to be going that way. So, ladies and gentlemen, what does that tell us about our theta? Ladies and gentlemen, theta is going to be 180 degrees. So that means cosine of theta is going to be -1. Okay, so that means we are going to wind up with negative work in the end. Okay, so, well, let's plot our scheme. Let's go through our goal and figure out what the heck we need to do here, because there's a lot of stuff that's going on. Well, I know I need to find work. Well, work of friction is going to be, that's supposed to be an F, but for some reason turned out to be a W. There we go. It's going to be the force of friction times the distance times cosine theta. Well, I'm trying to find work. I have distance, I've got theta, I'm good there. Well, I'm going to need to find my force of friction. Okay, well, I'm going to need to make an F net equation. Okay, so that's going to be, I'm going to have to do that. And once I'm there, I'll be able to find my F net equation. Let's do that. Okay, let's make our F net equation. Why not? So my F net is going to equal, well, what? Forces. We've done this before. Force of friction. There's only force of friction here, ladies and gentlemen. So our F net is going to equal the force of friction. Our F net is going to or force of friction is then therefore going to equal my MA. Okay. Well, I don't have acceleration. But guess what I do have? I've got my VI, I've got my VF, and I have the distance covered. So I can find acceleration with what equation? This one seemed to show up quite a bit lately. Your VF squared is equal VI squared plus your 2AD. So I don't write on my face. There we go. So that's the first thing we're going to have to do. Then that's the second. Then that's the third. So this is a 3-step equation, ladies and gentlemen. Okay, so let us begin with our step number 1. And that's going to be calculating our lovely acceleration. So my VF squared is equal to VI squared plus 2AD. Now VF is 0, so that's stop. And now I'm going to rearrange in order to get my acceleration. So I'm going to minus my VI squared over. So I'm going to wind up with negative VI squared is going to equal to AD. Well, I want to find my acceleration, so I am going to put in 2D. I divide by 2D. Okay. And we're going to scroll down. And so my acceleration is then going to equal negative VI squared divided by 2D. Okay. Now, I'm going to make a mistake here, and I want you guys to figure out what it is. Okay? All right. So what we're going to do is, well, my acceleration, well, my negative VI, so my negative, well, the speed this guy was starting out was 61, and that's going to be squared, and then I'm going to divide by 2, and the distance is my 42 meters. Okay. So I'm going to put this number into my calculator here, and then I'm going to, okay, so what I wind up with is going to be, okay, so let's look at that, negative 45.76 meters per second squared. That's really high. That's a super high number. Like that's just weird for a car to be slowing down 45 meters in a second like that. That's ridiculous. Where did I screw up? What was the mistake I told you guys I was going to make? If you said I forgot to convert my units, you are 100% correct. What I did not do is I did not convert my units. I did not convert that kilometers an hour into meters per second. So I am going to go back and do that. Now notice the process I went through there. I forgot to convert, and I looked at my answer, and then I thought logically about it. Well, 45 meters in a second, like that's huge. That's a huge distance, right? That's wider than the classroom. That's like a good chunk of a football field. Like and a car is not going to slow down that much distance in a second, not without you flinging out the windshield, which is why you wear seatbelts, by the way. Okay, so what I'm going to do is I'm going to go back and I'm going to fix my mistake. So I'm just going to rewrite my unit so I can do my unit analysis here. Okay, so it's kilometers per hour. And let's do time first. Why not? I'm going to cancel out my hours by converting that into seconds. Hours cancel. Seconds are on the bottom where I want them to be. And then I'm going to multiply that by my 10 to the 3 meters. So my meter is on the top. Divide that by the 1 kilometer. Kilometers cancel. I'm left with meters. And this is going to give me 16.94 ... meters per second. So now I've got my correct speed. That looks better. So I'm now going to go back and I'm going to fix this. Okay. So I'm going to erase that there. And we're going to go back and I'm now going to put in my 16.94 ... And now when I get my number, I'm going to erase this. And I'm going to put in my acceleration, which is actually going to be correct, of negative 3.418 meters per second squared. Okay, that's much more reasonable. A car can definitely slow down at that rate. That is much, much better. Okay. So much more reasonable for a car. So now, ladies and gentlemen, let us go and onto our step 2, which is using our F net equation in order to get our force of friction. So as you guys will remember earlier, we determined that our F net equation is our force of friction is equal to ma. So the mass of the car is 1385 multiplied by our negative 3.18. Okay. Oops, dropped a 4. Use all decimals that are in your calculator. Plonk those numbers in. That's step 2. And you're going to wind up with your force of friction as going to be negative 3.966 newtons. Okay. Now, the fact that we get a negative number here, that means we are going to be having an example of negative work. Okay. So, ladies and gentlemen, we are going to now do our step 3, which is going to be our, race, which is try not to make Wednesday Monday, and work is equal to force times distance times cosine theta. Now, this is where the tricky bit's going to be in, ladies and gentlemen. This, you do not carry in both negatives, okay? So we are going to keep this guy to be just the magnitude, okay? This guy, this force, is the magnitude or the size of the force. The cosine theta is going to be determining the job that that's doing, okay? So, and work is scalar, okay? So we don't need to be having our directions in there, okay? So our force is going to be, put the scalar quantity in, this is the magnitude of it. Drop my decimal. There we go. And then you can multiply that. I'm going to scroll down so I'm not writing on my face. Come on, scroll down. There you go. And then we're going to multiply that by the distance of which we calculated earlier, we're given earlier, which is 42 meters. And cosine theta, we already determined earlier, is -1. So your work due to friction is going to be -198,826 joules. That's J. And sig digs, ladies and gentlemen, units. Negative, showing that this is the job that the force is doing. It's in hindering displacement. And with sig digs, how many do I want? 2. We're going to convert this into scientific notation. So 1, 2, 3, 4, 5. And also notice I did round. Okay, so that's where my decimal would be. So then I go back and I look at these guys. Well, that would round up. So then that would force this guy to round up to 2.0. And there we go. Rocket. Okay, so ladies and gentlemen, our last question is kind of a bit of a break for you guys. It's a nice short question in comparison to these previous long ones. When I'm looking at the notes, it's like, oh, 4 pages. This will be a super short video. Apparently not. Okay, lots of concepts in this one. Lots of fun stuff. Okay, so here we have a 50 kilogram box. Is pulled 11 meters along a level surface by a rope. If the rope makes an angle of 35 degrees with the surface and the force exerted on the rope is 90 newtons. Okay, well, the force that's applied is 90 newtons. How much work is done on the box? Okay, well, let's draw ourselves a free body diagram. Well, here's our box. Here's the rope. the angle that it makes is 35 degrees. Well, remember from earlier in the video when we were talking about how why it's cosine theta? Well, here, ladies and gentlemen, theta is 35 degrees. Okay, so that's what we're going to be using. And that is our displacement vector. So I'm going to move our displacement vector down here again, just so that way it's easier to see. And if that's our speed, then that is going to be 35. Okay? All right, so let us do some calculations. Well, work, it's blue. It can be blue. Work is equal to force times distance times cosine theta. And the work, well, the force down the rope was 90 newtons. That's bothering me. There we go. And then our distance is 11 meters. And theta is 35. All right. Plunk them all in your calculator. 810.960 ... And now we are going to make sure we round that. We want 3 sig digs. So that is going to round up these guys. So we're going to wind up with 811 joules of work. The value is positive, and that makes sense because our velocity vector is going that way, and our force is contributing to that velocity. Okay, so ladies and gentlemen, I hope you guys enjoyed that. I did. It was a very fun video to make today. So what you guys have now is some practice problems to work on down at the bottom. And as always, do as many as you need to be comfortable with the material before you go take a crack at that assignment. I'm going to try and make a field trip video for you guys today. Those are fun. And I will kind of demonstrate some of the forces that we were looking at kind of in that earlier piece of the lesson. Okay, so ladies and gentlemen, I hope you guys have a good day and no fires, injuries, and explosions. We will talk to you guys later. I can't get to stop recording. There we go. Talk to you later, guys.